Testing. Okay, good morning to everyone. Let's start with recapping what we have done on Monday. Okay, there's something I want to clarify here. So first is the proof of this product of two integer modulo n group is cyclic and isomorphic to Z Mn if and only if M and N are coprime. Okay, or in other words, GCD is equals to 1. Okay, so I said that there are two kind of proof you can give is the contradiction or the direct proof, right? Okay, so this is for one direction. Okay, the direction is if I know that M and N are coprime, okay, then I can prove that it is cyclic. Okay, to prove a group is cyclic, what do you need to do? You need to find the generator. Okay, you want to find the generator that generate the groups. So what's the choice of generator we make here? Okay, we want to try and prove that it is generated by the generator of both groups, which is 1. Okay, 1, 1 in this case. Okay, so I want to prove that this is true. So how to prove that 1, 1 is the generator of this group? It means that the order of this element have to be equal to the order of the group. Okay, so that you can reach all the elements before you reach the identity, right? Okay. Okay. Any question? Reserve a question or no? No? Okay. So one way I do is through contradiction. Okay, so let's call the order of my generator P. Okay, I want to prove that P equals to Mn in this case. So let's say P cannot be 1. Okay, P cannot be 1 because if P is 1, it says that 1, 1 is just the identity, which is not true. Okay, so P cannot be 1. But if P equals to Mn, then we are done. Okay, this is the element with order Mn. But let's say these are not the order of P. What can P be? Okay, P is something in between Mn and 1. Okay, no, not only this, we know that by the branch theorems, this order have to divide the order of the group. Okay, so P have to divide Mn. So when does P divide Mn? So either P is M, P is N, or P is the divisor of M and N. Okay, thanks to eating for pointing out this, right? Okay, if P is less than Mn, but P want to divide M and N, okay, and then M and N are co-prime. So you either divide M, you either divide N, okay? Either you are M, either you are N, or either you are the divisor of M and N. So what are the two numbers are co-prime? You should have a number in your mind. For example, 1, 8 and 9. 8 and 9 are co-prime. So who divide 8 times 9? 8, 9, 2, 3. Okay, so these are the numbers you need to think about. Okay. So P, okay, the argument here is P cannot be a divisor that is strictly less than M, for example. Okay, if it's strictly less than M, what happened? It means that 1, 1 to P is the identity. Okay, but in the first place, you have Zm. Okay, can you go to 0 earlier than M or not? Okay, if P is a divisor, okay, that is strictly less than M, for example. Okay, M is which coordinate? Which M is the first coordinate. Okay, can 1 to the P equals to 0 if P less than M? No. Okay, so you cannot consider the divisor that are strictly less than M. Okay, so there's one choice left. Can P be M or not? Okay, can P be M? If P equals to M, what happens? You also get the first coordinate here, 1M equal to 0. Okay, but second coordinate, you also get 1M equal to 0 because P is the order of my 1, 1. Okay, so here is Zn. Okay, M and N are co-prime, meaning what? M cannot divide N. So can 1 to the power M go to 0? Cannot, right? Okay, so to go to 0 in Zn, what happened? You need to be order N for 1 or 2N, 3N, 4N, 5N. Okay, you need to be the multiple of N. But M and N are co-prime. Okay. It's not only not the multiple, they are co-prime as well. So meaning it cannot be M as well. Okay, so it cannot be any divisor of M. Okay, similarly, the same argument works if you prove that for P equals to M. Okay, so all the divisor of M doesn't work, all the divisor of N doesn't work, 1 doesn't work. Who else can divide them? It's just okay. So note that M times N, this number, right, is also the LCM of Mn. Okay, later we'll see this again. If I want to do it as a direct proof, what should I do? Okay, similarly, I want to show that 1, 1 is the generator. Okay, I want to prove that the order of P is Mn. Okay, so try and have a look. Okay, how does this two argument say the same thing with a different way? Okay, so we know that the order of 1, 1 must divide the order of the group. Okay, P divides Mn. So since the GCD of Mn is 1, there are only few possibilities here. Okay, either P equal to 1, P equal to Mn, or divisor of M and divisor of P. Okay, you can see that the argument here are following quite similar to the case of the contradiction. Okay, just that we rephrase it differently. Okay, so you discuss what happened. Can P equals to 1 happen or not? Okay, can P equal to Mn happen or not? Okay, can P divide M and P greater than 1 happen or not? Okay. Can P divide N and P greater than 1? Okay. Yeah, I think we should, let me see. So I think this P should be less than MN as well. Okay. How many of you have you read this document before you come? This is the one I put up yesterday day or 2 days ago. Anyone of you read this document yet? No one. Please read. My lecture note is very important to know what I'm thinking about, what I'm teaching about. Okay. Alongside with lecture notes, you should, textbook, you should read together with this lecture notes. Okay. Because sometimes I will emphasize different things other than in the textbook. So, I've talked to Xie Mei on Monday, right? Yeah, Monday. So I still can feel that you guys still prefer the teaching like I tell you what to do and then you do. Right? People tell you what to do, you just do. Okay, so I seriously want you to change this kind of thinking. Okay, this is spoon feed. Spoon feed. I tell you what to do, you do. Okay, this is what I don't want. Why I don't want to spoon feed here, at least. Okay, so this kind of spoon feeding education works before. Why? Because those times there are a lot of people that they don't have education. Okay, so to increase the level of education, we have to spoon feed. But nowadays, if you throw a stone to the society, you can easily hit a university student, and the stone will bounce back to another university student. What do I mean by this? There are too many university students already. So what makes you special? Okay, you need to develop an independent thinking here. Okay. Okay. 所以你要培养的是一个独立思维。我不想再用一些什么填鸭式的教育来教育你。Okay. So sometimes we will have confusion, okay, within the class, but we can try to find truth inside this confusion. Okay, within this confusion, we find what's the truth. This is similar in your society. Okay. Always you will heard people like quarreling, okay, arguing. But where's the truth? Can you determine what's the truth or not? For example, very easy. Maybe a couple, right? In this school, there's a lot of couples. They fight, they quarrel. Why? Why they quarrel? You don't like me. You don't love me anymore. Right? Who knows? It is just that yesterday I forgot to cook supper for you. And then you say, I don't like you anymore. Right? So how do you find truth within the confusion? Okay, so this is the skill you need. Particularly, this is the skill that this course can give you. Because pure maths is really abstract. How do you find truth in abstract? Okay. So you must be able to do reasoning. You need to be able to do reasoning. OK 了，你需要逻辑思维 ，OK， 来整理这些杂乱的思绪。OK 了 ，Does it make sense? Okay, I know it's tired. Of course, it's tired. You do exercise, you're tired or not? You go to gym, are you tired? Right. It's tired. It's tiring. Okay, but you need to tell yourself, I want to train you. Okay. Very good. At least should make time and talk to me. I think this thing should happen last semester. Only after one semester, you guys start thinking about this. But it's still not too late yet. because you still have a long way to go in your life. But you should change at one point. Okay. Yeah, so we can both improve together. Okay, so I really encourage you. I really encourage you read my lecture notes, read my assignment solution. Okay, compare to your solution, and then what's the difference between my expression and your expression? Okay, you need to learn. Okay. I also talked to Shemay why I give this hard question, argument question. Like for example, I gave 8 questions last week, last semester, last assignment, right? I haven't finished marking yet, okay, but I will try and discuss question today, and then try to give you back before Friday. Okay, Friday or before. And then I also have hard time marking. So why? So I torturing me for what? Right. So we want to try and work out something new, okay, together. Okay? Understand each other. What's your argument? What's my argument? Okay. What's wrong with your argument? What's wrong with my argument? Okay. Actually, in your class, I barely seen you guys arguing with me. Okay. I don't mean like quarreling with me, but you didn't stand with your own point. You know, you don't stand up with your own point. If you don't want to stand on your own point, who is going to protect your rights? 你要有你自己的立场，可以吗 ？OK。如果你觉得我们立场有冲突，我们就要开始讨论。OK 了，不是说我的立场是永远对的，或者你的立场是永远错的。OK， 所以你应该要，如果有分，你就要讨，但是你的分，我给不给是另外一件事情，但是你一定要来讨。如果是你的分 ，OK 了 ，OK。So if it's your mark, come and talk to me. Okay, okay. So this the other direction is what I a bit confused last time. So this direction is proving that if it is cyclic, okay, if I know the product group is cyclic, then the GCD is 1. Okay, so how we prove this? Actually, we prove this by contrapositive. Okay, we prove this by contrapositive. Last time I just directly say why there should be GCD 1 or why is it generated by 1, 1. But you can prove it by using contrapositive, meaning suppose that GCD of M and N is not 1. Okay, then I want to show that the product group is not cyclic. Okay, so this is the contrapositive part for this proof here. Okay, so quickly go through this proof. So if the GCD of M and N is greater than 1, okay, I can simply divide Mn using D, right? Because D divides M over N. Okay, M over N is a positive integer. Okay, so what does this mean? So this means that if I take any element, okay, in my Zm cross Zn, okay, so there's a typo again, I'll fix it. Okay, if this is an element of Zm cross Zn, okay, I can add M over N divided by D times. Okay, I'll get 0. Why? Do you know why? M over N is over D, Mn over D is an integer. But why if I add Mn over D times, I'll get the identity? Because this number is divided by M or N. Okay, it's divisible by M or N. Okay. Why? Because if when you divide M, okay, when you divide M, this D will divide N. Okay, so I can divide N. If I want to divide by N, okay, then this D will divide M again. So I can divide N. So in both position, okay, I can go to 0 together. Okay, because this order is divisible by m. Okay, so no element in RS can generate the entire group because you don't have element of order mn. Okay, all the elements have order less than or equal to mn over d. So there's no element can generate the entire group. So Zm cross Zn is not cyclic. No one can generate the group. Okay, because they go to 0 at mn over d times. This is an integer. Because d is a GCD of mn. So this is using a contrapositive. So far, any question regarding the group? Any question on that? Okay. If not, we can come back again. This one just extension. Okay, look at this. So look at this. Okay, so this definition last time I briefly go through. So what's the LCM? How to define LCM of a bunch of positive integer? It is the positive generator of the cyclic group of all common multiples of the Ri. Okay, that's the cyclic group of all integers divisible by each Ri. So I give an example here. For example, let's say I want to find what's the least common multiple of 2 and 4. Okay, use your normal knowledge. What's the least common multiple of 2 and 4? It is 4. Okay. So how do I see this from a group point of view? Okay. So I use 2 and 4. I consider all the common multiple. Okay, what are the all common multiple of 2 and 4? 8, 4, 8, and then 12, 16, and then 20, and go and so on. How about negative? What are the negative values are the common multiple? 4, minus 4, minus 8, minus 16, minus 20, and so on. Okay, who generate this group? This is what group? This is a subgroup of Z. Okay, we show that every subgroup of Z is cyclic. Okay, every subgroup of Z is cyclic. So who is the generator of this group? This is precisely the least common multiple. Okay, least common multiple will generate the group. And then we pick the positive one. We don't pick minus 4, we pick 4. Therefore, positive generator of cyclic group. Okay. So this example here, this theorem here, we quickly go through last time, and then we use it in the example to find the order of the group. Okay. So here says that what's the use of least common multiple here? Okay. So this least common multiple of Ri, okay, is actually the order of an n tuple. Okay. And then what's the property of this n tuple? You need to make sure that every AI here is the order of Ri. Okay. All these Ri here have order Ri. Okay. And then if you ask about what's the order of this element, the order of element is equal to the least common multiple of this Ri. Okay. Think about it. Think about it. Why? Okay. What does it mean by I have order Ri? Okay. This means that alpha 1 add to alpha 1 R1 times, you get to identity. A2 compose R2 times, you get to identity. A3 compose R3 times, it gets to identity. Okay. So you want to ask, what's the order of this element? Meaning, when does this order compose itself, it get back to identity? Okay. And the identity in the product groups is what? Identity in every position. So meaning you need to get to the identity together in the product group. Okay, when you compose with Excel. So if you compose R1 times in alpha 1, okay, to get to identity. A2 compose R2 times A2 identity. When does these two compose to identity together? When does these two compose to identity together? I give you an example. So let's look at one example. Z2 cross Z4. Okay. So what's the order of 1 in Z2? 2, right? Okay. What's the order of 1 in Z4? 4. Okay. So meaning Z2, so we will do a operation on itself, so meaning how should I write it? Maybe I write it here. Okay, so 1, 1 plus 1, 1, I'll get what? 0, 2. Okay, so meaning the first entry gets to 0 when you add every second time. Okay, but the second entry will get to 0 when you add every fourth time. Okay, so when does them go to 0 together? So here go to 0. So let me draw here. So on the first entry, it goes to 0 every second time. Okay, every second time. And then on the second entry, it goes to 0 every fourth time. Okay, so when does they go to 0 together? When do they go to 0 together? It's precisely the LCM of 2 and 4. Okay. So the least common multiple is the time when they go to 0 together. And this is how it is written in this proof here. Okay, so you need to make sure A1 go to 0, okay, A2 go to 0, A3 go to 0, up to AN, they have to go to 0 together. When do they go to 0 together? It is precisely the LCM of the order. Okay. Okay, if you cannot think about it, you should try example. Try more example. Maybe try Z3 cross Z6. Okay. Maybe you are a person that's hard to believe. Try examples. What is the order of 1, 1? Okay. In Z3 cross Z6. Okay. What's the order? Okay. How many times you need to compose? For example, sometimes you cannot just think about it. You need to do hands-on. Okay, I already told you. Abstract is not really abstract. It's really coming from a practical examples. Okay, you have to do examples. Okay, try more examples to see that, to convince yourself the same. You need to write. Okay, I tell with you cannot just listen. You need to write. Okay, you have to have muscle memory. So writing. You cannot just think. Okay, so we'll start with today's content. So last time we introduced this proposition here about product groups. Product. Okay. We want to prove the for statement here. So suppose we have a subgroup G. Okay, suppose we have a subgroup of G. Okay, call them H and K. H and K definitely intersect. Okay, why? Because we know that subgroup always contain an identity. Okay? They have to intersect. And then we try and combine the two groups, two subgroups, okay, H and K in G. It is clear that when you combine H and K, element is H and K, these elements should live in G as well, right? Because G is closed, right? G is closed in particular. So the problem is when you combine them, the point will sometimes be outside of h of k. H of k. Okay. So we will call the image, okay, under this map hk. Okay, so how about I make this smaller? Okay, we have this condition replaced by this picture here. Okay, we have h and k. Okay, there's an identity inside here, at least. Okay. And then we can consider the product of these two subgroups here. Okay. And then in my A theory produce a larger set, okay, which we call the HK. Okay. Maybe the pink one is H1 times K1, for example. Okay, I want to study this HK here. What happened to HK? Okay, what happened to HK? So the claim is if F is injective, then the intersection is just the identity. Okay. And if the intersection is identity, then F is injective. Okay. How about B? B shows that if H times K is a homomorphism, if and only if H and K commute. Okay, and if H is a normal subgroup of G, then HK is a subgroup of G. Okay, it's a subgroup of G. So if H is normal, okay, when you look at HK, it becomes a subgroup of G. Okay, so when is a HK a subgroup of G? When H is normal. Okay, one of them is normal. Is enough. And then when we have isomorphism, where this HK actually equal to original G, okay, if and only if this happen. Okay, you can imagine why will this happen. This condition here correspond to where the intersection of H intersect K is identity. This condition here correspond to the first point, which says that F is actually injective. Okay, so to talk about this isomorphism, right, what do you need? You need homomorphism and bijective. Okay, so the second point tells you when is it homomorphism. Okay, so you need this condition here. And then when is it injective? The intersection is identity. When is it surjective? When your set is equal to the whole G. Let's prove this. Or I let you try first. Maybe let you try first 5 minutes. Okay? Try any one of them. How you should start. 5 minutes. And let you try. Okay, you can discuss with your friend. I'll let you try first. You have 5 minutes. There are 1, 2, 3, 4, 5, 6, 7. 7 direction here. You need to prove these 4 points. Try to think about it. Discuss with your friend. Write down. Please write. Yeah, just pick anyone, any direction you like and try it. Yeah, this is a very good exercise to test whether you know injectivity or not. Okay, what is injectivity? What is homomorphism? Okay, what is normal subgroup? Okay, what is isomorphism? Just unfold the definition. You should see the proof. If you get the definition right, you are already halfway there. Okay. So what's a good start of the proof? A good start of a proof is to start with a definition. Okay. So we want to prove that F is injective if and only if the intersection is 1. Okay. So what is F? You need to write down what is your F. F is a map from the product set to G. Okay, or a product group. We define that this set actually can be endorsed as a group. Okay. And then what is the map? Okay. On element. What's the element in the product group, especially? Okay, it is just two doubles here. Okay, or the order pair. Hash k. Okay, what happened to hash k? I want to multiply them together. Okay, become a h times k in G. Okay, so this is a standard way to write down the map. Okay, you need to tell me what's the domain, what's the codomain. Okay, and then tell me how does the element, what does the element happen? Okay, under this map. So, which direction should we try first? Which direction you want to do first? Left to right or right to left? Left to right. Okay, let's do left to right. Okay. So left to right says what? If F is injective, then the intersection is 1. Okay. Any strategy you want to use? Kernel? What do you mean by kernel? Kernel equals to identity. Okay. So how do you show that? Still on the way. Okay. Still on the way. You want to use the kernel. Have we shown that this is a homomorphism yet? I haven't quite shown this is a homomorphism yet. Okay. A homomorphism is injective if and only if the kernel is the identity, right? Okay. So what can you do? Okay, what can you do? You see, there's some trick in proving, right? Okay. So let's write down what we want to do first. So suppose F is injective. We want to show that H intersect K is the identity. Okay. So let's discuss what you need to do if you want to do this. So what you need to do in here, you need to do set equality here. Okay, you need to do set equalities here. So meaning you need to prove two direction here. Okay, two direction, two subset inclusion. So you need to show that one is in the intersection. Okay, this one is very clear. Every subgroup has the intersection. But why the intersection of H intersect K has only identity? Okay. So meaning you take every X in here, the intersection, X has to be equal to the identity. Okay, how on earth you're going to do this? You just know something about the function is injective, right? Yeah, so we can try and use contrapositive. Okay, suppose the result is not true, then the assumption is not true. Okay, we can use contrapositive. Why? Because contrapositive will give us extra thing to work with. Okay, if I suppose that my intersection is not identity, that means there's other thing other than identity inside my group I can play with. Okay, so by using contrapositive, you create extra condition for you. Okay. Suppose, okay, for the sake of contradiction, okay, I will phrase it as contradiction. Okay, you can phrase it as try phrase the proof as contrapositive. Okay, you can phrase it as contrapositive. I'll phrase it as contradiction because I already start with since I already start with F is injective. So for the sake of contradiction, okay, suppose that the intersection is not just the identity. Okay, this means what? Then there exists X is not equal to identity, which is in the intersection. Okay, which is in the intersection. But what did we prove last time? Intersection of subgroup is a subgroup. Meaning if X is in there, X inverse is also in there. Okay. So by assignment question, H intersect K is a subgroup, which implies that X inverse is in H intersect K. Okay. Are we good now? Are we good now? What can I do? Can you imagine what do I want to do next? Then f of x and x inverse is x times x inverse, which is the identity. Okay, but we know that identity will go to identity as well, because you just plug number in 1 1 here. Okay, 1 1 go to identity. X inverse also go to identity. This means what? This means f is not injective. Okay, because 1 1 go to identity, x inverse 1 also go to identity. Okay, two different elements go to the same elements, meaning f is not injective. So then this is true, and f11 also go to identity, contradicting the assumption that f is injective. Okay. Okay. Feel free to stop me if you have any question. Okay, the other direction. So suppose that the intersection is only the identity. Okay. We want to show that f is injective. So how to show f is injective? That is, if f of h1 k1 equals to f of h2 k2, then what? h1 k1 has to equal to h2, okay, for all h2 in h, h1 h2 in h, for all k1 k2 in k. Okay or not? Fx equals to fy implies x equals to y. Okay, so to this end, what do we do? So let h1 k1. So we take any h1 k1 and h2 k2, okay, in hk, such that what? Such that f of them is the same. Meaning, if I multiply them, they are the same. Okay, so this is the condition I want, I suppose. Okay, what is f? F just multiply the order pair together. Okay, and then what happened here? What happened here? What can you play around with this equality here? What can you do? Any idea? Huh? Inverse. Okay, so what inverse you want to take? You can move all the h to one side and all the k to the other side. Right? So then you can play around with it first by cancellation. What do I get? Maybe first I get h2 inverse h1 of k1 equals to k2. Okay, and then I can move again. h2 inverse h1 equals to k2 times k1 inverse. Okay. What's the good of doing this? On the right hand side, what do you get? 1. Who said 1? Who said 1? Who said? You? Why is it 1? Yeah, why is the identity? The identity? Sorry? Oh yeah, before that, this terms here, is it identity or not? Not sure, right? Because K2 might be different from K1. Not sure. So K2 is an element, K1 is another element maybe. Okay, and then the inverse of K1. But we know that this element is always in K, right? Because K is a subgroup, it is closed. So you can take product with inverses and the element. And then on the left hand side, what do you have? H2 inverse with H1, which is in H as well, right? Because everything here is in H. So this guy is in H and in K. So it is in H and K. So this element has to equal to identity. Okay, this element has to equal to identity because in our intersection we only have identity. So by assumption, okay, since H2 inverse H1 equals to H2 inverse K1 is in H intercept K, okay, by assumption, they have to equal to 1. Okay, if they equal to 1, what happens? So this means H2 inverse H1 equals to 1. K1 times K1, K2 times K1 inverse equal to 1. That is H2, H1 equals to H2 and K2 equals to K1. Okay, which is what we want. Okay. Or you want another step, maybe you want H1, K1, the ordered pair of H1, K1 equals to the ordered pair of H2, K2. How do you compare the two ordered pair? You compare them entry-wise. Okay, you compare the ordered pair entry-wise. Okay, entry-wise. Okay. How about we finish all the proof before we finish 3 of them and then we take a break. Last one is a bit long. All right. So how about this one? This is an all homomorphism if and only if they commute. Okay, if and only if they commute. Let's write down what's happened. Okay, what happened if F have to be a homomorphism? Okay, a good start with definition is a hardware to finish the proof. Okay, so let's take 2 elements inside my group. Okay, then what? Then you can do 2 computation here, right? What are the 2 computation you need to do to check homomorphism? FAB and FA times FB. Okay, so in our case here is F of A is what? Okay, H1, K1. F of B is H2, K2. Okay, and F of AB. Okay, F of AB is what? F of H1, K1 times H2, K2. Okay. So on the left hand side, what do you get first? Ryan, what do you get? H1, H2, K1, K2. Well, say again, I didn't hear. What's the left hand side? What is this term here? Sorry, say again, slower a bit. Repeat first. So what do you get? F? F or H? Then this one. K1, K2. Is this right? Let someone else to check. E, is this right or not? Do you get this? H1, H2, K1, K2. You confirm, correct? Like this is a 造谣 already. 造谣. Someone confirmed the 谣言 already. 造谣. So what is it? Very important. You need to know what is right or wrong. If you know some wrong and then people confirm it, and then everyone will spread like that. So this is not good. Okay. Never mind, it's okay. We learn, okay? We learn. So what is f of H1K1? What's this map here? Yeah, this one you should get just H1K1. Okay, how about f of H2K2? H2K2, right? So if you multiply two elements together, what do you get? H1K1, H2K2. Okay, so this is the what you get from left hand side. Okay, so if you are unsure, you say unsure. Don't think that what people say is right. You know, okay? Very important, very serious problem actually. This is a serious problem in this society. Okay, please avoid this. This is wrong. Okay, next. On the right hand side, what do we get? So we first delete, right? Yeah, I delete. Yeah, I cancel it out. Huh? What did you say? Okay, so how about the left hand side, right hand side? Okay, you need to compose the two elements inside first. Okay, how do you do product inside a group? Yeah, okay, we define it as a component wise. What do I get? Let me ask one. So Stephen, what do I get when I compose H1, K1, H2, K2 together? Yes. H1, H2, and then comma with K1, K2. Okay, good. So this is a ordered pairs already. Okay, so we can map using F. Okay, what do we get? H1, H2, K1, and K2. Okay, so what's the difference between these two expressions here? What's the difference? What's the difference between these two? We want to equate these two, right? If this is a homomorphism, these two have to equal. So what's the difference between the last expression? Sorry? Sorry? Louder a bit. Yeah, so the two elements in the middle swap. Okay, so you want to make sure the two of them is the same. Meaning what? K1H2 is equal to H2K1. Okay, but this has to be true for all the H2 and K1. Okay, so meaning all the elements have to satisfy HKH equal to HK. Okay, so this is true. But what is true? So make a same here. So K1, so H1 K2 K1 K2 equals to H1 K1 H2 K2 if and only if H2 K1 equals to K1 H2. Okay, and this is true for all H2 K1. Okay, meaning all the elements inside H2. And this is an if and only. So if you want this side to be true, then you need to make sure the middle term to be true. If the middle term can swap, then I will get the equality on the homomorphism. Okay, so this is the if and only. Okay, straight away. Okay, so if you get the good definition, you have a good start already. Okay, make sure you get the right definition. Okay, let's do C and then we take a break. Okay. So C. H is a normal subgroup of G, then HK is a subgroup of G. Okay. So we just start with writing out what we have. So suppose that H is normal in G. And then we want to show that HK is a subgroup of G. What's the meaning of HK as a subgroup of G? Let me write it aside here. Meaning what? You take HK here, okay? Identity have to be in there. Okay, why identity is in there? Because both of them have identity. Right? And then the identity of the group is just E times Z. Okay. You can get the identity from E times Z. Why is it close? Is it close or not? Meaning, if I take H1K1, H2K2 multiply together, is it in HK? Can I write everything as product of H and product of K? Cannot. If can meaning what? I need to somehow move the H2 to the front. Okay. Inverse exists or not? Is HK inverse live in HK or not? HK inverse is what? K inverse, H inverse. But K inverse, H inverse is not in HK. Okay. So seems like this obvious choice doesn't work. What to do? Okay. So is there a way I can swap these two positions or not? Can I swap K and H or not? Okay, so this is the question. Can I swap H and K? Wait. H is normal. Okay, so how does H is normal telling us anything useful? Huh? Okay. Okay, good. So let's proceed. So last time, what do we say? When H is normal, okay, can I tell anything about the coset or not? What happened to the coset of H? What happened to the coset of the normal subgroup? Okay, you need to flick back into the proposition before. Okay, you forgot. Is what? Yes. Okay, if you have a normal subgroup, your left coset and your right coset are equal. Okay. By proposition before, okay, all the left and right coset are equal. Okay, all the left and right coset are equal. So meaning what? Meaning KH equals to HK. Okay? Because this equality is true for all little k. Okay? So you can look at the whole set here. Okay? So then this is good. Then I claim that this is good. Okay, why is this good? Why is this good? Okay, so if you take any element from HK, okay, I write it as a set notation. You can write it as an element notation. So HK, what can I do? I can replace KH with HK. Okay, I can replace, for example, H2K2 equals to K3H3, for example. Okay, because I have a set equality here. KH equals to HK. Okay, every element K1, H1 can be written as H2, K2. Okay, so I can swap. But I change my expense is I change to another product. Okay, but I can swap position now. Okay, and then how about inverse? How about inverse? If I have HK inverse, what is it? Just now I said that this is K inverse, H inverse. Okay, this thing is in where? Is in KH. But every KH is equals to HK. So meaning I can write K inverse H inverse in some H4, K4. I don't know what is it. Okay, but this is enough. We just want to show that inverse at least. Okay. Okay, I write it in the set notation form. You can try and write it in the elements notation form. Okay, maybe you can find another element that swap the position of pressure. Okay, any question on this? Yeah. HK is Abelian or not? Okay, to talk about Abelian, right, you need to talk about law of composition. So you need to ask whether this product group is a law of composition or not. Okay. So why is it a law of composition? So law of composition is a map from X cross X to X. Okay. So what's the set that contains the subgroup here? So where does H live? Where does K live? Where does H times K live? All these three elements need to live in the same set to talk about law of composition. Or you talk about Abelian. Okay. So where does this guy live? Sorry? Sure, it's in G. Yeah, sure, okay. They live in G. No, they are element of what? They're supposed to be an element of a set called X. Element of what? Okay, element of who? Okay, so this set here should be a set of group. Right? H is a group, K is a group, H times K is also a group. Okay, can you define a law of composition of groups or not? Okay, if I define the law of composition of group as product group, okay, I can multiply group and get another group. Okay, this is good. Do I have, I don't need identity, right, LLC? Yeah. So if you define product group as a multiplication of group, then I think you can say that it is commutative on this condition where H is normal. But H is normal, and then this H and K has to be as a subgroup of G. It's not just random two groups. Yeah, so it's quite restrictive. But we need to make sure that H and K both are the subgroup of one group. You cannot random just take any subgroup from any places. Yeah, you cannot take subgroup of different group and then you product them together. We show that this is a group, but do we know about this property or not? I don't know. Okay, so this is quite restrictive because H and K have to both live inside the same group. Because what property we are using here, this is actually the coset. It's a coset. So coset meaning you are like partitioning something. It's the thing where they both live in. Yeah. But although you cannot use Abelian precisely, but you can somehow think that they could be the coset. Something with H. But just be careful when you use the word. Yeah, because it's not precise. But it's one way to think about it. Okay, any other question? No? Clear? Okay. So if it is clear, don't think that you understand. You have to practice. Okay, you have to practice. Practice and write it out yourself. Okay, let's take a break and then we will resume 9:34. Return 考到今天教的。
都另外一个
哪个？
这个我是觉得F1 X 等于 F1 就够了。
F1 X 等于 Fx1，
对，
什么意思？什么意思？
一乘以 X 等于 X 乘以 E 啊，因为 identity 啊，这不是你的地方。
也是说，可以啊。哎，喂，等一下。哦，对，它 intersect 的 section 可以，没问题。
我有一个问题是，
问题
当一个就是讲关于
哪个？
下面啊，就是有一个 H
在哪？
应该是讲 H2 inverse H E，
Yeah
然后等于 identity 嘛，这样是代表 H2 inverse 是可以等于 H E。
这个可以可以。
代表 H，
喂，等下给我猜，可以啊，怎么？
现在代表 H，
因为
等于 H E，
对
H2 等于 H E 的话，就是代表他们只能等于是一样。
没有，他们是一样的 element 的话，肯定他们的 inverse 是一样，因为 inverse 是 unique 的，记得吗？每个 element 有一个 unique 的，
对，
所以你肯定会拿到 H inverse 等于 H2 inverse。
现在代表 H 1等于 H2， 也就是我讲 H2 inverse 也可以乘以 H2，
and then
然后就等于 H1 乘以 H1 inverse， 所以这两个是一样的，这两个 element 是同一个
咯，因为你没有你乘了 inverse H2 乘了 H1 inverse 肯定是 identity 吗 ？H1 乘了 H1 inverse 也是 identity 哦，因为你只是 identity 一样罢了，所以其实你好像不知道了一些东西已经不见了 H2 H1 的资料已经不见了，因为你乘了 inverse 过后大家都去了 identity，你已经不知道发生什么东西。
刚好是有一个开 BRO，
哪里？
在下面，这边那个是这个，你写了3个 K
啊，你可以直接跟我讲啊，社恐，不用社恐了，没有恐了，就你对我吧，其他人不用紧。呀，
开玩笑，
有吗？对吗？
没有，所以你刚才那个 HK 的 HH 嘛，
啊，对，
不是可是它不是 commutative 的那个意思，
就是讲你要讲 commutative 还是什么之类，你要 define 那个 law of computation 先嘛，你才可以开始。
我们讲最直接就讲我们那个 program，我们这边 KH 跟 HK 啊，如果AB 在 KH 里面，那么 BA 也在里面。
再一次，
如果 AB 在 KH 里面，那么
AB 有没有在
HK 里面一样嘛？所以它应该要在里面。
在 HK 里面，在 HK 里面。
所以
BA 会不会也在 KH 里面
BA 会不会也在 HK 里面？不一定，不知道，它只是 equal to something 3B2A2 这样吧，我不知道是谁，它是 set equality，我不知道它是谁，所以 that's why 呢，我 introduce 一个新的东西，我不知道他是谁，可能在，可能不在，我不知道。
它这个 set 的 equality 只是告诉你
哦，和 element 一样，可是它不一定要对到。
对到 in your sense
啊哈哈哈。
啊，
不会是这个
不一定
AB
是用
对到那个
旧的东西做出来
对对
的东西，
对对对，它可能是
很有可能都是用新的东西做出。呀，这个是非常重要的一个东西。
对啊，因为我以为是因为B 在 K 那种就是，
嗯，maybe 我写一下。
对，以前刚好一样，那就可以
Yeah
啊，
但是它不是所有在 K 里面跟所有在 H 里面都可以做 product，但是这样子H1 K1 怎么不可以在里面？一定会在
哦，一定会在咯，
会在
一定会在，但是不
不会
一定等于
等于这个
啊，
不会
不一定等于。
等于这个。
有没有？我先推过来窃取他们的知识。
没有窃取，那公共的公共资源。哎，对哦，哎，忘记啊。
Okay, let me take attendance. So Venus, 乐天好呀，规则，当然，严苛呀，sorry, OK，严苛啊，please be aware with the deadline next time, okay? Yeah, don't leave until last day. Steven, 至于金星、森林 ，OK，海人啊，金波还有嘞，不是啊，OK，喂，弟兄，诶，英奇，OK，一可以的，雪岩啊，家业，OK，离开呀，晕，OK，晕加 OK，不错，一定，因为 what happen to you？第一个天赋啊，渊博，很艳，宁静，OK。宁静you do much better in the assignment. Please keep it up. Hello, 宁静，Yeah, please keep it up. 董洁，宜州，冰云，柳琴，柳琴 not here. 柳琴 not here. Sing. Don't know. Don't know or not sing. 大家 not here. Is she sick? You think so? Okay. 真诚，说你，好说你，OK，这样。一，子谦，子轩，呀，莹莹， Grace, Yep, Calvin, Sue, Chelsea, Brian, okay, Nelly, May, the end. Okay. Okay, let's start again. Okay, what? So, okay, a very important concept here just now I want to emphasize. When I say two set is equal, right? Okay, K1 doesn't necessarily K1 H1 doesn't necessarily equal to H1 K1. Okay, it is most probably equal to some other H2 K2. Okay, we just have equality on set. Okay, so equality of set maybe will shuffle the elements around. Okay, maybe we'll shuffle the elements around. But H1 and K1 is definitely in HK, but they might not be equal. Okay, this is a very important point of equality on set. Okay, you need to know. Should we prove D here? You want to prove D? D is a bit long. Okay, let's prove D. Right to left. Okay. If I have all these property here, can I prove that F is isomorphic or not? Okay. Can I do it? Who? In second. Okay. So if I already know the intersection is one, means what? I know that F is injective already. I know that HK is equal to G, meaning my F is surjective. Okay, because my F combine the image of my F is HK. And image equals to the codomain, meaning the F is surjective. So there's only one thing left to prove. F is what? I know F is injective. I know F is surjective. I need F to be homomorphism. Okay. I need F to be homomorphism. Need F to be homomorphism. So right to left. So H intersect K equals to identity implies F is injective by part A, we proved just now. And if the image, okay, so this is the image of the map, multiplication map. Okay, I call the F as a multiplication map because we multiply elements together. If the image of the multiplication map equals to G, this means F is surjective. Okay, this is a normal function theory. Okay, only thing we left to prove is F is a homomorphism. Okay, so the last thing we want to show is F is a homomorphism. Okay, so F is homomorphism means what? There's part B, right? There's a part here. If for all H and K, HK equals to KH. HK equals to KH. HK equals to KH.
But just now, what do we have? If I know one of them is normal, okay, if I know one of them is normal, I know that as the level of set hk equals to kh. At the level of set, we know that kh equals to h. Okay, but now at the level of set, they are equal, meaning k1, h1 might be equal to h2, k2. But to be a homomorphism, we demand more. What do we want? We want k1, h1 equals to h1, k1. Okay. Okay. So that's why you see there's an extra condition here. K is also normal. Both h and k are normal. Okay, somehow will give us this stronger condition here. KH has to commute. Okay, KH commute. Okay. How should we prove this? Okay. So I want to show that F is a homomorphism by part A, part B, part B. By part B, we need to show that for all K and H, for all K and K, H and K, and H and H, HK equals to KH. Okay, this is what we want. So we want to show that this thing commute. Okay, this thing commute. So what to do? What can we do? What can we do here? We can try and look at one thing. Okay, so we can move everything to one side, right? In particular, we can look at this object here. HK, H inverse, K inverse. Okay, we can ask whether this thing equals to identity or not. Okay, I mean, I just move KH to the other side. Okay, consider this element. Can we see where this guy come from? Okay, if this guy equals to identity, then we know that HK and KH commute. Okay, this thing here is what we call the commutator. Okay, if the commutator equals to 1, then the two elements commute. Okay, if the commutator of H and K equals to 1, then it commutes. Okay. Okay, what's this element? There are two ways to look at this element here. Okay, so one way is you can group the first 3 terms together, or you can group the last 3 terms together. Okay, you can group the first 3 terms together, you can group the last 3 terms together. Why? This is the associativity of the group. Okay, I can group like this. So what's the advantage of grouping like this? Okay, so first grouping here, this is what? Conjugate of K. Okay, K is in a normal subgroup. You conjugate by H. H is also an element in G. So this whole thing live in where? K. Okay, this whole thing live in K. Okay, so you have something live in K multiplied by something in K, right? So the whole thing here is in K. Okay, how about here? If I group, look at the conjugate of H inverse. Where does this live? In H. Why? Because H is normal. Okay, so we have the condition that K is normal, and H is normal. Okay. So what? So you see, on the right hand side is everything in K. Alright, everything is in K. On the right hand, in the left hand side we have everything in K. In the right hand side we have everything in H. Okay. But what do we assume? What do we assume? We assume that the intersection is 1. Okay, so meaning this commutator have to equals to 1. So since the intersection only contains 1, this commutator has to equal to 1. Okay, which implies hk equals to kh by multiplying kh on both sides. Okay or not? Okay. Does it make sense? Make sense? Okay. Just feel free to ask. If you lost, please go and find the definition and the proposition. Okay. How about the other direction? The other direction, what do you need? If I have isomorphism, okay, I want to show that all these properties hold. Okay. So the first two is obvious. Whenever it's injective, your intersection is 1. Alright, this is by part 1, if and only if, 2 direction. And then hk equals to g is just definition of surjectivity. So what you really need to show is h and k are normal. Okay, I think we don't want to do this in class, okay, because it's kind of tedious. You can try and work it out. Okay, try and work it out why h and k are normal. Okay, I will provide in lecture notes. Okay, can or not? Yeah, the last bit I link to you. Not too hard, I guess. I'll write it out. Okay. Okay, prove that h and k are actually normal. Okay. Can or not? Is it okay? Okay, I'm trying to prove that they are normal. From definition again. And now we want to go to interesting stuff now. Okay, so we want to prove that there exists only 2 groups of order 4 in this world. Okay, so first is Z4, the other one is Z2 cross Z2. Okay, or I will sometimes write this as a cyclic group, C2 cross C2 with composition. They are isomorphic. Okay, so let's prove this. On the right left hand side, also I can write as a cyclic group. Okay, generated by 1 element. You know what's the law of composition for cyclic group? You know? Law of composition for cyclic group is assumed to be just a multiplication. Okay, and then since I already tell you this is a cyclic group, meaning this is generated by 1 element with order 4. Okay, then you can generate the whole group. Okay, meaning you can do 4 times and then come back to identity. Okay, yeah. This information I tell you is cyclic, tell you the order, then it's enough. Okay, the law of composition is multiplication, and it's enough to see the whole group. You need to understand this. Okay, try and write it out. Okay, if you don't understand, please ask. Let's try and write it out. Okay, I want to prove this. Okay, so let's prove this. So we start with any group. Okay, I hand you a group of order 4. Okay, can you define any law of composition you like, such that it is closed? That's all. Closed, got identity, got inverse.
Okay, I hand you 4 things. Go and build whatever LLC you like. Okay, as long as you have identity is closed and then the inverse exists. Okay, build anything you like. And then you tell me what have you built. Okay, my answer to you is up to isomorphism, these are the only 2 things you can build. Okay, so this is the strength of this proof here. Okay, so how to prove this? Let G be a group of order 4. Okay, by Lagrange theorem, what do you know? By the corollary of Lagrange theorem, you know that the order of any element, okay, in the group must divide 4. Okay, must divide 4. So there are how many things can divide 4? 3 things. 1, 2, and 4. Okay, 1, 2, and 4. 1, 2, and 4, right? So if 1 is it possible? Identity, can you have 4 identity inside the same group or not? Cannot, right? This becomes a degenerate group. Okay, so it cannot be 1. So there's only 2 and 4 you can consider. Okay, so let's consider 4 first. So there are 2 cases to consider, right? The third case is degenerate, we throw away. Okay. So case 1, G contains an element of order 4. Okay. So I claim that if it contains an element of order 4, then G has to be a cyclic subgroup of order 4. Can you see why or not? If you have an element of order 4, what can you consider? You can automatically consider a subgroup generated by this element, which we call a cyclic subgroup. Okay, this cyclic subgroup is order 4, right? Because you have to go to the 4th order before you return to identity. Okay. If you return before that, then this is not the order. Okay. So you have to go to different elements before it goes to identity. Okay. This is what we have proven last time. Okay. So it has to go to different elements. Okay, before it goes back to identity. So your subgroup has order 4, your original group has order 4, then there should be the same group. Okay, this is what we have shown last time. If you have question, you can ask also. No question or no? No. Okay, I'm happy. Happy? Make sure you're happy. If not happy, you have to say. Okay, I'm not happy, I also say. So you're not happy, you also say. Okay, yeah. Okay, so if everyone happy about case 1, then we move to case 2. So case 2 is what? So case 2 is there's no order of 4 elements in there already. Okay, this means that every element of G, okay, except the identity as order 2. Okay, note that a priori, so before we have this reasoning, we don't know there's Z2 cross Z2 or not. Okay, we know there's Z2 cross Z2. We don't know whether this is Z2 cross Z2. We want to move to the stage that we know that this group is actually isomorphic to Z2 cross Z2. Okay. So what do we do? So anything we can work out from here. We only know that the element is order 2. What does anything special about this order 2 thing? Yeah, transposition is one of the examples. What is the inverse of the transposition? Itself. Okay, is this true in general? Is this true in general or not? Why? You see, suppose x squared equals to identity. Then I can multiply inverse on both sides. Okay, we will get x equals to x inverse.
So this is not only true for transposition, this is true for all the elements of order 2. Okay, so this is what I want you to see from this kind of abstract math thingy. So you need to try and abstract more and more properties out from examples. Okay. At first, you only know that 1, 2, the inverse of 1, 2 is 1, 2. But actually, whoa, if the element of order 2, the inverse is actually also equals to the element itself. Okay, as long as your element is order 2. Okay, and then what? And then what else we can play around? So let's just take any two elements in G. Okay, let's take any two elements in G. Then we can ask about how about xy, right? How about xy? Xy is another element in G. Okay, this element is also has order 2 because we said that every element has order 2 as long as it is not identity. Okay, as long as xy is not identity, this guy has order 2. Okay, as long as this is not identity. Okay, this shows what? Again, this shows what? Again, this shows what? This shows what? What's order 2 about? This shows what? This shows that xy equals to it inverse. It inverse is what? Xy inverse, which is y inverse x inverse. Fair enough. Okay. But what is y inverse x inverse? It is actually yx because all the elements in G has order 2. Okay. So meaning what? Actually, all the elements commute with each other. Okay, all the elements commute with each other. So this shows that x and y commute. Okay, so x and y commute mean what? Meaning the group is actually abelian. Okay, G is abelian. Okay, G is abelian. So what? Abelian group. What's good about abelian group? What's good about abelian group? So you see, let me point something to you. So why we prove this? We're gonna use D. Okay, just now we prove A, B, C, D. Okay, the most important thing is actually D. Okay, everything points to D. So we want to use D here. Right, remember, the only one group we left with is a product group. Okay, Z2 cross Z2 or C2 cross C2. But to get this hash and K, what do we need to know? We need to know that hash K is actually a normal subgroup. Okay, so can we build a normal subgroup or not? From what we know just now, any subgroup you want to take. Any subgroup we can take here. Remember, the easiest subgroup you can make is a cyclic subgroup. So you take a subgroup, take an element, and then use that element to generate a group. Okay. Any two elements we have so far have looked at here. Any two elements so far we have looked at here. So actually, this x and y not equals to 1. It doesn't want to take something equals to identity. Any two elements we so far have looked at here. X and y. Okay, so we can look at the normal subgroup generated we can look at the cyclic subgroup generated by X and Y respectively. Okay, but these are the subgroup in the abelian group. Remember last time I talked about what's the relationship between center and normal. Center is the thing that commute with everyone, right? Okay, if your group is abelian, everything is in the center because everything commutes with each other. Okay, and then normal, what's the relation between normal subgroup and the center? Center is a normal subgroup. Okay, so meaning normal subgroup is center is a normal subgroup. Okay, so every subgroup in the abelian is actually normal. Okay, every subgroup in the abelian group is actually normal because everything is in the center. So every element in the abelian group is in the center of the group. So the center of the group is normal. So meaning every subgroup in abelian group is normal. Since every subgroup in an abelian group is normal, we can look at the cyclic subgroup generated by X and Y are also normal. Okay, this is also okay. So by part D, what do you need? You need that the intersection is the identity. Okay, and then the intersection, the multiplication of these two groups is actually the whole. Can you see why the first property here is true? What? Hey, don't wait for my answer. Think. Don't wait for my answer. I won't give you answer. Think. Why one is true? Can S and Y be the same? Cannot, right? If Y, S and Y is the same, then they are just the one subgroup. Okay, I want to take a different one. Because there are four things inside my group. Remember, there are four things inside my group. One is identity, take away already. Only three more things you can think about. Okay, I call it X1 for two of them. Okay, so X and Y is not the same. But inside this normal subgroup, how many elements? No, each of them. Each of them have two, right? I mean, for each of them, the cyclic subgroup have two elements. Identity and X, identity and Y. X and Y is not the same already. What else left? With the what else left? What else left inside this intersection? So you are taking a two element set, intersection of two element set. Here got what? Identity. This one? Identity. But out of four, I pick two different X, Y. So what left inside the identity? So what's the thing inside this identity? Cannot understand. So so here. Let me write down. So here is the set with E and X. Here is the set with E and Y. So what's the intersection? E, right? Because we said that X and Y is not the same as time. Okay. How about 2? Is it true that if I multiply the two set together, I get the whole set? Huh? True, right? So what kind of combination I can get? E, Y, X, Y. 4 elements. can get. Okay. Okay. 4 elements I can get. Sorry. And my G has 4 elements. Okay. We know that X, Y are not the same. Okay. So the only possibility is whether X, Y can be equal to E, X or Y or not. If they are not equal, then this is a new thing. Yeah. Wait. Oh, sorry. So here put, oh, sorry. Yeah. Okay. So the thing you need to consider here whether XY a new element. Okay, is XY a new element here? Okay. So can XY equals to E or not? Can XY equals to X or not? Can XY equals to Y or not? Okay. Can or not? Huh? No, right? Yeah, think about it. Why cannot? Unsure. And then okay, so let's look at these two cases here. These two cases is easier. If these two cases hold, that means Y is identity or X is identity. Then this is contradiction. If this one hold, what happens? X is equal to Y inverse. That means X equal to Y. Contradiction. Okay. We start with different. Okay. Okay. So XY is a new thing. Okay. X and Y is different, then E is the identity. So we get 4 elements here. So we know that this G is actually isomorphic to the cyclic subgroup generated by X cross with cyclic subgroup generated by Y. Okay. Okay. So this is order 4 cases. So in general, right? In general, okay, we can prove that every finitely generated abelian group is isomorphic to the direct product of the following cyclic group. So maybe there are some, what we call here is the torsion group. Torsion. So torsion group here is like there's a finite order for your element. Okay, cross with the element with infinite order. Okay, finite order elements cross with infinite order elements. We won't prove this, but this proof also uses the ABCD proposition we use just now. Can be proved. Quite long. Okay or not? What time is it? 9:56. Okay, 9:56. Before we finish, I want to quickly go over the assignment first. Let me find my assignment solution. Okay, so the test will test up to today's content. Okay, today's content. But focus on the LCM part. For the last part, focus on the LCM. Okay, so I'm happier in this assignment because I see most of you have improved. So please keep up your work, okay? Improving on your writings, understanding the question, what the question was, okay? So please keep up your work. And then, so far, not too big problem on question 1. Question 2, not too hard. Let me see which question. Okay, for question 3. For question 3, you guys match up the order. Okay, some of you match up the order. So you just get the cyclicity just by applying chip. That's not true. Okay, because that is just a property of function. What you need to do is you need to take an element in the core domain and then show that that can be written as a power of some generator. Okay, this is what you need to do. You cannot just say I have P of AN and I get PA to the power n, and then everything there can be written PA to the power n. No, you need subjectivity. Subjectivity tells you what you can do to every element in the core domain. You need that. Okay, otherwise you're just looking at the image on it. Okay, so we want the image of the map equal to the core domain. So this is what the subjectivity will give you. Question 4, surprisingly, most of you can get it. But one problem is some of you just look at one particular isomorphism. You construct a particular isomorphism, say that it doesn't work, then it doesn't work. How about I send elements to different other isomorphism. Does it work? Other map, does it work or not? Okay, so do you consider all the possibility? Okay, if you consider all the possibility, well, is there a single reason why they don't work? Okay, you need to think about it. You see, my answer is so short. I don't know how long is yours. Try and compare. Okay, try and compare. Shorten your answer. Okay. And then question 5. Question 5 so far okay. Question 6. Okay, question 6 got some problem here. So the problem is to construct the counterexample. Okay, counterexample. I saw some of you didn't cite your friend, is it? Didn't reference your friend. I'll send out an email soon. Okay, if you don't cite your friend. Okay, so this example here, you guys play a nice trick. What do I mean by a nice trick? You somehow use the first counterexample to show the second counterexample. Okay, I mean I didn't forbidden you to use that. Okay, in this question, but you can actually find a subgroup. You can actually find a proper subgroup J and H to make this work. I have an example here. You can actually use proper subgroup. Okay, you don't need to use the whole tree. Because you guys just start with a non-normal one and then intercept, of course, the non-normal one. No, it's not normal, right? I mean, I let you pass, but what I want to tell you is you can actually find a proper subgroup. Okay, 2 proper subgroup that works. Okay, yeah. Try and read this answer here. 7. Okay, 7 here. There's little mistake people tend to make is after you found an element to the power p, its identity, you straight away say that, oh, that element is order p. Have you considered all the multiple that's less than p or not? You need to consider it. Okay. For example, what is the thing that divides 1 and p? It's just 1. So you need to discuss why 1 doesn't work. Okay. If 1 works, that means the original element have smaller order. This is the contradiction you need to write. Okay, you cannot just say, oh, this element to the order to the power p is identity. I conclude this element has order p. You have to tell me why all the smaller power cannot be the identity. Okay, when you take it. Number 8. 8. Most of you do it okay. Okay, just that sometimes the proof is quite long because you can see that my part A is quite straightforward here. Okay, I just straight away use the because it partitioned the group, right? So when it partition the group, it's actually a equivalence relation. Okay, I can write down what's the equivalence relation. But you guys show it using set, right? Okay, it's okay. You can show it using set, but it's quite long, and then some of you just leave out some of the part. Okay, you didn't write it completely. And then this is okay. So you should compare with your solution and my solution. Okay. Can you write shorter or not in your solution? Okay. Can you write it cleaner? Okay. Part B. Part B actually quite interesting. Some of you showed it the other way. Some of you use some portion map. Yeah, portion map. Portion group we will map later, probably next week. Yeah, so far it's like this. Any question about assignment? Understood. So next Monday, right? Please come 10 minutes earlier to prepare, okay? So we will start sharp at 9. We will have reading times about 10 minutes. Okay, I'll let you read. And then we will start exam 1.5 hours. And then we'll finish exam. So please come at 8:50 to prepare. Okay, next Monday. How many questions? How many questions? I forgot, but around 7, I think. Yeah. Not many. No more. No. If there's more question, there's less sub-question. I mean, it's the same. So, okay, how I design the question is like 100 marks. 1 mark almost equivalent to 1 minute. Okay, so 1 minute you need to write 1 point. Okay, so 100 marks equal to 100 minutes, which is which is what? 1 hour and a half, right? Yeah, it's more than 9. Yeah, yes, it's less. Correct, it's less. So it's less. So that's why I asked you to come earlier so that maybe we can have extension. Yeah. Okay. Yeah. Otherwise, the exam is too short.